started with our seminar. Okay, sorry. We're gonna get started with our speaker this week. So joining us this week is Patrick Milner, and he'll be talking about modeling the effects of AFT shoes on metatarsal stress, a finite element approach. Patrick is currently a master's student in biomedical engineering here at the University of Calgary. And he also did his undergraduate degree here at the University of Calgary. And his honors thesis was on understanding the effect of novel knee brace technology on knee flexion and valgus angles during lateral motion. And a fun fact about Patrick is that prior to starting his university, he worked as a professional hiking guide and a wilderness first responder certified by the Association of Canadian Mountain Guides. So if you need any advice for the mountains, he's the one to go to. So thanks, and we're looking forward to your talk.
Perfect. Thank you so much. Can you hear me all the way in the back? Amazing, thank you. So, like you mentioned, today I'm going to be discussing the effects of advanced footwear technology on metatarsal stress, specifically with a finite element modeling approach. If we look at the kind of shoes that individuals are wearing at the top end of racing today, they look nothing like they did 20 years ago. We've essentially created a new class of footwear, which in the industry, we are now referring to as advanced footwear technologies or AFTs. These kinds of shoes are things like the Nike Vaporfly, or more recently, the Nike Alphafly, which have been used in multiple different races and challenges, such as the Ineos 159 challenge or the Nike Breaking 2. There are a few different things that go into these shoes that make them unique and more advanced than your everyday running shoe. A few of the key advancements that these kinds of shoes have are a highly resilient midsole foam. So they return a lot of the energy that you put into it every stride. They're also very compliant. So there's a lot of compression every step. With this, the stack height also tends to be higher than a traditional racing flat. With the shoe geometry as well, there's also a larger toe spring. So the toe spring in running shoes is defined as the curvature between the pivot point of the shoe and the toe of the shoe. Also embedded within the midsole is this carbon fiber plate, which adds a lot of rigidity to the shoe and makes it much stiffer than the running shoes that you might be wearing right now, or the running shoes that you wore even a few years ago. With these unique changes to the construction of the shoe, there are some changes in how individuals are running when they are wearing AFT shoes. Specifically, there's an observed change in cadence in both treadmill and overground running, but notably on treadmill running, there's a reduction in cadence. So how many steps per minute someone is taking at a fixed speed. There's also a decrease in the metatarsal phalangeal joint angle. So this MTP joint is the joint in between your toes and your metatarsals. So think of it as your foot flexion. If you take a step and bend over your toes, that's your MTP joint flexion right there. There's also an observed reduction in forefoot pressures. So a combination of this midsole foam and carbon fiber plate are reducing any points of high pressure in this forefoot region. Individuals are also using AFT shoes at an increasing frequency, not only at the highest level of competition, but also as recreational runners. In this recent preprint that just came out, there was a survey of recreational runners after they finish a local race, and they were asked, do you wear AFT shoes and how often do you wear them? Every single person that chose to respond to the survey ran in AFT shoes at least once per week, with 68% running in them once a week, 27% running in them up to 3 times a week, and 5% running in them up to 7 times a week. So pretty much for every single session. With these shoes not just being used for racing anymore, but also for everyday training, this question starts to come up as to whether or not the shoes and the way they're influencing our running style, is this predisposing us to certain types of injuries? So these shoes are very different from your normal running shoe that you associate in your head as conventional running shoe. Are these changes to the construction causing injury? And this is a question that's being asked in the general public as well. If you just go on Google and search up carbon fiber shoes or AFT shoes and injury, everything will come up as saying these shoes are injuring individuals. Most of them are linking AFT shoes to like stress injuries, so thinking stress fractures. But if you dig a little bit deeper into all of these articles, they all link back to the same exact publication. So this was a case study that came out last year in 2023, making the bold claim that carbon fiber shoes are leading to bone stress injuries. But there are a few limitations with this one article that everything else seems to be building on. With this case study, there was a very small sample size of n equals 5. And out of these 5, nearly all of them had additional risk factors that would make them likely to develop a stress fracture, regardless of what shoe they were running. If we look at the actual characteristics of this n equals 5 sample, we have a good distribution in age ranging from 17 to 38 years old, pretty even split between males and females. However, if we start to look at some additional risk factors, 3 out of the 5 had had a previous stress fracture in their foot, which again predisposes them to future stress fractures. And 3 of them had never worn AFT shoes before, or were relatively new to running in this type of footwear. One individual bought a pair of these carbon fiber shoes and proceeded to run a marathon the next day in them. Definitely not what I would recommend for any shoe. And again, starts to make us question the interpretation of these results. If we look at more recently published work that looks to try and understand how AFT shoes are actually loading the foot, we start to see some conflicting evidence against this. This study came out just this year, was looking at how carbon fiber plate thickness and curvature would affect peak plantar pressures. The results of this were not only that carbon fiber plates decreased peak plantar pressure, but they also continued to decrease this plantar pressure as a function of thickness. So as the carbon fiber plate got thicker, the pressure under this forefoot region decreased. When we look at AFT shoes and injuries, we have this really limited amount of literature that we can look at to try and understand what is happening at a skeletal level and what could be explaining either a cause of injury or a potential reduction in injury. And this is what motivated us to do our work and our study to try and explain what the actual mechanical loading of AFT type shoes are on the human skeleton. Specifically, we chose to look at the metatarsals, and we chose this for a couple of reasons. First of all, like I mentioned earlier, with the addition of the carbon fiber plate in AFT shoes, we have this significant change to the flexion of the MTP joint, so the metatarsal phalangeal joint. This would suggest that when individuals are running in the shoe, there might be a different loading environment at this joint, which could change the mechanical loading of the metatarsals. Additionally, the metatarsals are an area of concern for stress fractures in running, being the second most likely bone to develop a stress fracture in the running population. In terms of understanding the cause or potential of stress fractures, there's really 2 things that need to be considered. And this is stress magnitude. So how much load is the bone experiencing and how many cycles is the bone experiencing loading for? If we think about an individual who's running the same amount of distance in one shoe versus another, really the big thing we want to look at to try and see what shoe is safer or more dangerous would be stress magnitude. And that's what we focused on for the majority of our work. To try and make a preliminary model or an initial understanding of how AFT shoes are loading the skeleton, we developed and implemented this first study protocol. And this was largely Bill and Claudiane that collected this data, so thank you very much for that. Made the start of my master's a lot quicker and easier. So for this study protocol, we had 10 male recreational runners, shoe size 10, who performed repeated overground running tasks just downstairs in the main lab. And this was at a fixed speed. We took 5 trials for each participant in each shoe condition. Shoe condition was also randomized. While individuals were running, we collected a few different points of data from them. We collected plantar pressure through the use of extensor insoles, as well as motion capture of the lower right limb. Following the in-lab visit, we had a subset of our participants receive a weight-bearing CT scan over at the McKeg Institute. For our shoe conditions for this study, we had 2 different shoes, an AFT shoe and a conventional running shoe. For our AFT shoe, we selected the Vaporfly. This is one of the more well-known examples of a carbon fiber shoe or an AFT shoe, and generally has more publications on it. It's also more familiar to individuals who come in the lab that this is an AFT shoe. For our control, we chose the Nike React shoe. This is more of a high mileage type running shoe. And again, it has quite contrasting material properties to the Vaporfly. If we look at longitudinal stiffness, with the addition of the carbon fiber plate, the Nike Vaporfly is much stiffer than the Nike React. In addition, with this newly developed foam, it has a higher energy return. So as you compress the foam, more energy is coming out of it every stride. Additionally, because the Vaporfly is largely designed for racing and high performance, it is a much lighter shoe. For this study, we did not control for shoe weight and instead decided to have the most real world application possible. So if an individual were to do their run in one shoe versus the other, we wanted to model that as is. To measure the shoe-foot interaction, we used extensor pressure insoles, and we segmented this into regions of interest. We did that by creating 5 different regions for the metatarsals. So this would be where the metatarsal heads are making contact with the insole or the shoe, and then 3 separate regions for the toes. Toes 1 and 2 had their own region on the insole, and toes 3, 4, and 5 all shared this 3rd toe segment that then was subdivided for analysis later on. Now to look at some of the data that we're actually getting from this study. Similar to what was published before, we are observing a reduction in peak pressure in this forefoot region when individuals are running in the Vaporfly. Here we have a graph of pressure, so plantar pressure, specifically in this red forefoot region, so the entire forefoot in our 2 shoes, the React in blue and the Vaporfly in red. All of the gray lines are individual responses to these 2 different shoe conditions. After analysis, we did find a significant reduction in this peak pressure. However, we could take it a step further and look at the pressure reduction across each of these individual metatarsal regions. So under each metatarsal head, what is happening to the actual plantar load or plantar forces coming out of this? So here we have the same y-axis pressure, and then we have each of the metatarsal regions across the x-axis. Same 2 shoe conditions, In blue, we have the Nike React. In red, we have the Nike Vaporfly. Here, we found a significant reduction in plantar pressure under metatarsals 1, 2, and 3, suggesting that some of this pressure reduction is happening more on the medial side of the foot. Another variable that we wanted to replicate from previous studies was this MTP flexion angle. So again, the flexion of the metatarsals relative to the toes. Every single participant saw a decrease in this angle when running in the Vaporfly shoe. This is again largely due to the stiffness of the carbon fiber plate in the shoe. To move toward a bit more of an advanced analysis, we wanted to start calculating the forces acting on the metatarsal, specifically the metatarsal head. And we started off by doing a musculoskeletal model as our first approach. Goal here was to determine the axial force acting on the metatarsal, as well as the moment at the midpoint, which gives us an understanding as to the flexion and load that the metatarsal is under. To do this, we needed to first find the orientation of the metatarsal relative to the toes using our MTP flexion angle, as well as calculating the resting angle of the metatarsal. So using our weight-bearing CT scans, we were able to determine what the resting angle of the metatarsal was in our 2 shoe conditions, and then add on our flexion angle to determine, again, the orientation of the metatarsal relative to the toes. Once we had the orientation, we're able to map some of our plantar forces onto here, specifically the force acting under the toe region and the force acting directly under the metatarsals. With an inverse dynamics approach, we can then calculate the axial and perpendicular force components acting on the metatarsal head. From here, we can move a step further and turn this perpendicular force component into a moment calculation about the midpoint of the metatarsal. And again, the reason we do this is just to give us a little more insight as to what's happening at this midpoint, as the midpoint of the metatarsal tends to be the region that a stress fracture would develop. When we look at the results of our musculoskeletal model, we're going to start by looking at the axial force, the force acting directly through the metatarsal. Here we have force on the y-axis, and again, metatarsal number moving across the x-axis. Same 2 shoe conditions, the Nike React and Nike Vaporfly. And here, again, we see a significant reduction in this force in metatarsals 1, 2, and 3. Similar to what we are seeing in our plantar pressure results. However, when we go to look at the moments between our 2 shoe conditions, we found no significant difference between our 2 shoes. To move toward a deeper understanding and an actual understanding of how the skeleton is responding and being loaded, we developed a finite element model to again calculate this mechanical load. To do this, we created a mesh from our CT scan data and then applied our forces. So again, our axial and perpendicular force components from our musculoskeletal model to this mesh to estimate our bone stresses. For this study, we had 1 participant receive a weight-bearing CT scan. So this is really nice because individuals can apply load to their feet wearing each of our shoe conditions. So they had the Nike React on 1 foot, Nike Vaporfly on the other, and they can load themselves, it's weight-bearing, and we can capture an image of what the foot is doing in the shoe. From here, we segmented out our bones of interest. So the metatarsals, we identified all of these and created a mesh, so an object, a 3D object that we could then map our forces onto. So we had 1 set of geometry that we applied subject-specific forces to. all of our subjects. All of our finite element modeling was done in Abacus, where we took our metatarsal, we fixed the base of the metatarsal in 3 dimensions. We did not allow any movement at the base and applied all the loads to the head of the metatarsal. This resulted in us being able to calculate or estimate the stress distribution within the metatarsal. When it comes to measuring stress out of a finite element model, we're not left with just a single value, but rather a value for every single element within this model. This results in a stress distribution a little like something here, where we again have the react in the blue line and the vapor fly in the red line. Here across the x-axis, we have the stress that elements are under, and on the y-axis, we have the number of elements that correspond to that stress level. From here, we decided to look at the 97.5% stress interval. So not looking at the element with the absolute maximum stress, but rather one that encompasses 97.5% stress. Looking at the results from our finite element model, we found a significant decrease in stress in the first and second metatarsal. So here we have stress on the y-axis, metatarsal number moving across the x-axis, and again our 2 shoe conditions of react and vapor fly. To summarize this first set of results, when individuals were running in this AFT shoe, we observed decreases in peak plantar pressure, not only in the forefoot region, but also in 3 out of the 5 metatarsal regions we mapped. We saw a decrease in axial force from our musculoskeletal model. We saw a decrease in the MTP joint angle, as well as decreases in metatarsal stress for the first and second metatarsals. These results are suggesting that AFT shoes did not increase the magnitude of stress experienced by the metatarsal for any of the metatarsals, and in fact, significantly reduced the stress in MET1 and MET2. This is in contradiction to the assumptions of that N=5 case study that made the claim that bone stress was increasing in AFT shoes. The results of this point to the exact opposite. However, this first study did have a couple limitations. We only looked at male runners in this first study, and it only looked at an acute running intervention. So it had no data points over the duration of a prolonged run. And that's what we hope to answer with our study 2, which we are just beginning to analyze now, and we have some preliminary data for. For this study, we had 14 female recreational runners of US women's size 7 through 9, in which they performed a 1-hour submaximal run in each of the shoe conditions. Prior to doing this 1-hour run in the lab, we performed a ramp test to determine what their submaximal paces would be so that everyone could be running at roughly the same intensity. For intensities, we selected 65% of heart rate reserve for the first 45 minutes and 75% heart rate reserve for the last 15 minutes. Again, just to have consistent loading across all of our participants. While individuals were running on the treadmill, we collected roughly the same data that we collected from the first study, which was plantar pressure through the same sensor insoles. They were mapped the same way, as well as, again, motion capture of the lower right limb. Following their in-lab visits, this is where the study gets a little bit different. We are collecting subject-specific scans. So in contrast to study 1, every single individual in this study will be receiving their own scan and their own geometry. We use the same 2 shoe conditions for this. So the Vaporfly and the Nike React. When it came to analyzing the data of our long run, we first wanted to see if there was any changes in the loading environment for the metatarsals over the duration of the run. And one of the things that could change the loading of the metatarsals, again, would be this MTP joint flexion angle. We observed similar results to study 1, where we found this quite large difference between our two shoe conditions, between the React and the Vaporfly. However, we didn't necessarily notice any change over the duration of a run. So the joint flexion angles that we observed at the start of the run stayed relatively consistent all the way through this 45-minute time interval. We also looked at cadence because this will influence the amount of loading cycles that an individual experiences. If we can think back all the way to the start of the presentation, the two things that are going to affect stress fracture risk or probability are stress magnitude and the amount of loading cycles. We observed an initial difference between our two shoe conditions. However, as the run progressed, the cadence, so the amount of steps per minute that someone is taking, they both trended down a little bit and also converge. So the cadence between the two shoes at the end of the 45 minutes were very similar. We also performed our musculoskeletal model for an initial subgroup of these participants, starting with the 0 minute of the run. So right when they're starting the run. And we saw nearly identical results to what we saw in study 1, so our overground acute running intervention. We have force on the y-axis. We have our first and second metatarsals, so our metatarsals of interest, where we saw change in our first study for these two shoe conditions. And again, we saw a significant difference in both of these. Looking next at our 45-minute time interval, so a prolonged time point into the run, we are still seeing these differences between our two shoe conditions with ever so slightly of improved performance in the Vaporfly. So this difference increased by about 1 to 2% depending on the metatarsals. But we're still seeing this significant decrease, which is really promising. When it comes to the perpendicular force component, which is responsible for the midpoint bending moment that we looked at before, we again are seeing no change between this perpendicular force in our two shoe conditions. When we look at the results of this, or the preliminary results of this extended running study, we found that regardless of what time point we're looking at, we're seeing the same decrease in axial force, as well as this decrease in metatarsal phalangeal joint angle. Based on these two results being consistent between study 1 and study 2, we can hypothesize that we would also be seeing a decrease in metatarsal stress once we start running our finite element models for this study. Summary, for both studies across men and women, we saw reductions in the stress experienced by the first and second metatarsals. These reductions in stress or metatarsal forces might also be becoming more pronounced following a long run. And as our study progresses and as we start analyzing more and more of our participants, it's possible that we see a time effect start to emerge as well. Despite what was originally claimed last year in that case study, it seems that as more and more results are coming out, not only from our lab, but also from others, AFT shoes do not appear to be increasing the load experienced by the metatarsals. In fact, due to the unique geometry and mechanical properties of the shoes, it appears that we are consistently observing decreases in plantar pressure, as well as decreases in the stress experienced by the metatarsals. Overall, this would suggest that there may potentially be an injury prevention aspect to these shoes as well, in which, due to this reduced stress, there's a decreased likelihood of fracture development. assuming the same amount of loading cycles. Thank you very much. I'd like to thank both the Edwards Group as well as Biomechanik Sport and Health Research for all their support and supervision throughout this project, as well as FitFlop for providing funding for Study 2 and NSERC for providing our funding for our CT scans. Thank you very much.
Just going back to how you compared your results to that case study. I can't remember the exact injuries, but I think they were slightly different than injuries to the metatarsals. So how would your data, how would you compare it to that? Like, can you explain more?
Yeah.
How it?
So the case study specifically looked at navicular stress fractures, which are a bit of a rare occurrence in running. You don't see too many. Metatarsals are the more common ones, and that's what we did look at. If we think about the anatomy of the foot and where the navicular is stationed next to the metatarsals, it would be expected that if we have a decrease in this axial force component, as well as just the general stress in the metatarsal, there'd be less being transferred to the navicular, less stress experienced there the whole way down the foot. And that's also the explanation provided in that case study. They were essentially saying the carbon fiber plate was adding too much stiffness. The bones and the whole arch of the foot were all pressing together and causing this navicular stress fracture. But because we aren't seeing that increased force and stress in the metatarsal, it would be logical to extend that to say that there isn't this kind of increased force in the arch of the foot.
Question back there and then we just.
I have very limited biomechanical knowledge, I just want to preface that,
Okay.
but, I was just wondering, like, for the two shoes that you were comparing, did they have the same, like, arch support, and how would that change the outcomes, like, would that create more stress fractures?
Yeah, so they are quite different in their geometry. So even things like drop, which like if we can think of a shoe midsole as a ramp, the drop would be the difference between the forefoot foam and the rear foot foam. There are differences in that. So the foot will be sitting at a different angle in our two shoes. And that's why we did our CT scans in each shoe to figure out how is the metatarsal being aligned. And that is kind of how we accounted for this difference. If we think very, very generally, shoes that have a greater drop will see an increase in axial force of the metatarsal just because you're angled more steeply. Shoes that are flatter might see an increase in this perpendicular force component, but there are more factors that can go into that, like the stiffness of the shoe, how cushioned or how compressive the foam is. All of these things will, I guess, influence metatarsal stress as well.
And what about with flat-footed person to like a little higher, because you can account for that?
We did not account for the geometries of people's arches. It is possible that some people would respond to some shoes better than others. Our hope is that with Study 2 and using this individualized modeling approach in which we collect everyone's metatarsal geometry and foot shape, we can start to account for some of those differences in arches and again, try and get even more accurate than Study 1 did.
Yes, Matt. A very naive question. You know, you talked initially about the foam, the compliance of the foam, and that it's resilient and compliant, and then we talked about the fiber plate being stiff. So how all of this, so it's not just the stiffness, so how all of this affect the shoe and then the performance during running?
Yeah, so the shoes are very interesting and unique compared to what you think of as a conventional running shoe. And you're right that this foam is very soft, but with the addition of the carbon fiber plate, now we have this longitudinal stiffness aspect. However, if we still compress from top down, you can squeeze it quite far, even just with your hands. And because of the high energy return of the foam, we see an improvement in performance. Additionally, because of the longitudinal stiffness, so from toe to heel, and a bit of, of a spring effect almost at the MTP joint, you can see a bit of a work reduction there and improved performance. Did that answer your question?
Did you speculate or is that based on knowledge?
The foam improves performance with the energy return. That's been proven with the changes in work.
Which paper?
I can send you or I can show you my references at next week's individual meeting if you'd like. I believe I've presented them a couple of times at this point, but I don't know off the top of my head. I'm sorry.
So we had a question from Matt.
Yeah, thanks for that. Do you mind, there was a part one metatarsal stress figure. And something kind of stood out to me and I don't know, I was wondering if you could comment on it. It was the one that showed the individual responses.
This one?
Yeah, and I guess what I kind of noticed is like this distinct pattern with metatarsal 2, where it sort of seems like there's a threshold there where everybody above a certain level are all showing a really similar pattern. And it got me thinking I mean, I know it's a small sample size, it could be just an artifact and just random chance that's the case, but do you think that there's some sort of relationship there where the effects of this depends on stress, meaning that if you are low, it has less of an impact, but if you happen to be somebody who puts a lot of stress through the metatarsal, the impact's actually more significant that way? What, just initial thoughts on that, or?
Yeah, so there's a lot of speculation on my part in this answer, but my initial impression of that would be that at low load levels, you're not fully benefiting from the stiffness of the plate.
Right.
And you're still just in this kind of foam benefit area where you compress the foam a little bit, but you're not really stressing this carbon fiber plate. With individuals that weigh a little more or that run a little bit harder, if you apply more plantar force through your foot, now you're starting to benefit from the plate a little bit more compared to an individual that's not really loading their foot that much.
So you think there could be something there where the potential for stress reduction depends on?
Potentially, with this sample size, it's really hard to say, like again, n equals 10. But my speculation would be that at higher load levels, the plate would be providing more of the benefit than at low load levels.
And just one more little small question, isn't the fifth metatarsal fracture the big problem for runners?
Second and fifth are kind of problem areas. The second mainly because it's so long and thin compared to the other ones. But in my opinion, anywhere where we can be reducing bone stress in the metatarsals would be a good change, or even as long as we're not observing a positive, well, an increase in stress, but we're seeing improvement in performance, that would still be a good thing for a good result.
All right, so for this study where you talked about the advanced footwear technology, I was just wondering at the very beginning, you showed me a study that where there's only 5 participants. How did that study came to be like, so like everybody like kind of sold to the findings of that study, and you said they were like,
Oh, this one?
yeah, I think I was just confused like how everyone got so sold to the idea that findings were accurate.
So it was really just the first one that I'm aware of that made any type of claim that these shoes are causing injury or not causing injury. So carbon fiber shoes as a whole are pretty big buzzword or a hot topic in footwear research. So they put forth this first set of case studies and made this really bold claim that these shoes are causing injuries. With any kind of magazine or public article, like all the rest of these are, it's really easy to sell this kind of controversial opinion or just this hot idea that the shoes that everyone loves are now causing individuals injury. So they all grabbed onto this first research paper and built their articles from there.
Yeah, I'm following, yeah.
Go for it.
So this article is only like a year old. I was just wondering, do you have any more background information as to like when these shoes were like first used, or like when they were first developed, like when did they start being massively used?
Yeah, we're getting close to 8 years now, I think, that the Vaporfly's been around. You can correct me if I'm wrong, Ashna, but I think it's about 8 years.
Yeah, 2017, 18 as well.
Yeah, we got online questions. Go ahead, Robert.
Thanks, Patrick. I found this fascinating talk. I'm interested in the control levels for this, and by controls, I'm thinking people running barefoot. There are many people in hot countries, North Australia and Ethiopia come to mind, where many people have never worn a shoe, even today, even into their late teens. And so I'm thinking that there are two. I'm looking at your plots, and I'm thinking the two controls. One, the people who have never worn shoes into adulthood, and they have a broader foot from memory. And if you and I took our shoes off, if we ran barefoot, and to put some perspective into those metatarsal pressures and see what's the difference between, true barefoot running and these two shoe positions. Do you have any, is that well known, or do you have any concept of what that would look like?
Yeah, so I wouldn't say it's well known, like as far as I'm aware of, there's no research that looks to compare barefoot shoes and AFT shoes at this point. There are, however, some papers that look at metatarsal stress in barefoot shoes versus conventional running shoes. And those did find that for individuals who weren't accustomed to barefoot running, so like conventional shoe wearers that then switched to barefoot shoes, they saw an increase in metatarsal stress when running in barefoot shoes. However, when individuals have only ever run barefoot, like you mentioned, there's some changes to the foot geometry, there's changes to bone density. Individuals are able to adapt to this new style of running. And I think that applies to really any shoe. You're able to adapt to the loads that you experience relatively well. So I think an individual that exclusively ran barefoot and was then switched into an AFT shoe, I think they might actually see an even greater decrease in stress just because of a result of all the benefits of AFT shoes for conventional runners. But now you have a stronger bone, you have a healthier foot that's now able to leverage this technology even further.
So you think that the running in the Vaporfly would be healthier for the foot than the person who has spent a lifetime running barefoot? That was sort of where I was wondering.
Yeah, I wouldn't say healthier. I think it would be different. So like I mentioned really briefly there, my belief and kind of the idea that's being suggested in terms of stress fracture risk is that generally we're able to handle the loads that we are used to and adjusted for. So if an individual were to switch shoes suddenly or increase their mileage suddenly, there may be a risk of injury there. But if an individual gradually transitions to a new shoe or a new training program, that they're able to perform, well, be at kind of a neutral risk of injury, regardless of what shoe they're using, as long as they are adjusted and acclimatized to that condition.
Right. Okay. Thank you.
Yeah, you're welcome. Thank you.
I have a quick question, and then we'll move on to witnesses. So you said it showed that you're reducing peak pressures with these carbon fiber plated shoes, the
Yes.
Vaporflies compared to the control.
Yeah.
Why do you think that's happening?
Why do I think the pressure is being reduced in this forefoot region? Specifically thinking about, like, if we just look at the foam properties, and this would be like the thinnest point here on this slide, it would be that we have this highly compliant foam. I believe that it's able to mitigate hotspot formation a little bit, so as you have a area of high potential pressure, the foam deforms and you redistribute that a little bit better. With the addition of the carbon fiber plate, I think this takes it a step further, and instead of having a area of high pressure localization as the pressure is being distributed through the foam, again, this carbon fiber plate is reducing the metatarsal angle. Now your metatarsals aren't going straight into the foam, but rather at a reduced angle, a little more distributed in that sense. If I explain that satisfactorily.
Do you know if there are studies on the muscle activity around the foot and how?
Yeah, so there are some papers that look at calf muscle activity and tibialis anterior. There haven't, to my knowledge, been any studies that look at any of the muscles in the foot, like little stabilizer muscles. Those are a little bit harder to look at just because we have the whole shoe wrapped around the foot, but it definitely is an area that needs to be looked at further to understand how the muscles are responding to running in these types of shoes.
For your study one, how do you think the results would change if you had individual geometries for all those bones?
Yeah, so we did run a very brief analysis to see if there would be differences using individual models. And we found differences in stress magnitude between the different models that we used, but the statistical results were the same regardless of if we used individual or a single model. So individuals that decrease their stress in the vaporfly still decrease their stress in the vaporfly, regardless of if we use an individual model or a single model.
And as a follow-up to that, so what would be the benefit of using multiple scans in your second study?
So the benefit of using multiple scans in our second study would be to strengthen our musculoskeletal model a little bit. So instead of just using one set of measurements for everyone, now we have everyone's own metatarsal length. They're with the actual interaction of the foot tendons, we can measure that and have more accurate musculoskeletal model, which may influence our end results, as well as if we start to have this conversation about injury risk, this is when stress magnitude becomes a lot more important. So we're not just looking at differences in stress anymore, but actual cycles till failure. And if we want to calculate or estimate cycles till failure, it would be beneficial to have more accurate stress measurements for both shoe conditions.
Before I go to, I actually have a follow-up to that one. I was wondering if your peak pressures and the plant pressure measurements are an input to your model, then why, and you're reducing those, why do we need a musculoskeletal, like the scan and then a model to predict that your loads are gonna go down? If the input's going down, wouldn't you expect the loads?
We would, yes. And again, this is just moving toward a deeper understanding of how the shoes are influencing the skeleton. If we just wanted to know are forces being reduced, we can just look at plantar pressure and see we have this decrease under these regions. We can assume that forces experienced by the skeleton are also reducing. But like, I guess the last question, if we want to actually answer this question about injury risk, this is when we have to start considering stress magnitude, differences in stress magnitude, and that can really only be accomplished with this finite element approach.
Then we had a question right there.
Yeah. So my question was that where you were like gathering the data. So did you notice that the landing of the foot is more likely on the heel or on the toe?
So we didn't control for forefoot, rear foot running. And I wasn't actually in the room for the data collection of study one. However, based on the pressure data that we do have, we can calculate whether someone is a forefoot runner or a rear foot runner. At the higher speeds of study 1, so 4 meters per second is a little bit quicker than individuals ran in study 2. So more of them were forefoot runners or midfoot runners. For study 2, we're seeing predominantly rear foot runners in that
And
data set.
I assume that it affects the stress that you are analyzing.
It does and doesn't, so it'll affect the curve of our stress. But for the model that we're using and the methods that we're using, we calculate stress across multiple time points throughout the stance. So we don't just pick out of one measurement and say, this is the plunger force that we're using as our input. Instead, we have a measurement at each 10% of stance and use that as an input, calculate bone stress at that point, calculate bone stress 20%, 30%, 40%. So even if someone is a rear foot runner or forefoot runner, we're still able to capture their moment of peak stress regardless of shooting or running style.
Just because this figure's been on screen for a while.
Yeah.
It seems like that increasing the thickness, you get, looks like a pretty linear drop. And it looks like it would continue if you go thicker than that. Do you think that is due to the fact that that empty bending angle is reducing and continually reducing? And with that, do you think that's kind of the main driver of your results?
I think largely, yes. One limitation of this study was it was primarily computer modeling. So n=1, everything was calculated in static or SolidWorks. So they just adjusted plate thickness in SolidWorks. And this is likely why we're seeing such linear results in this study. I do believe, however, though, that we would see similar results in like a real life n=15 study, where as carbon fiber plate thickness increases, we see somewhat linear decreases because of, again, like you mentioned, that reduction in MTP.
Yes. We're gonna be the devil's advocate here.
Yes.
So you showed that the study by Stanford, and they have n=5.
Yes.
And so for yours, it's n=10. So do you think it's a strong finding? So why didn't you do this more time?
So that's why we tested more for our second study. We're still collecting more, so we're gonna be between 15 and 20 for study number 2, once that one's fully finished. With our n=10, we did find like strong, significant differences just in our measurements, as well as a relatively large effect size. And for some of our variables, when we consider individual response for move to our stress measures here. For 9 out of our 10 participants, we saw a decrease in metatarsal stress. So it's not like we are looking at this pretty, I guess, random spread. The majority of our participants, a very strong majority, are responding in a similar fashion. And our hopes are, with a larger sample size, that we'll continue seeing this trend with a strong majority of our participants responding favorably to Vaporfly shoe.
So what is the 97.5, sorry, 97.5% reduction? Because I thought I understood everything in your model, except when you got to the 97.5 reduction.
So this is just talking about an interval on our stress distribution. So instead of just looking at the absolute peak value, which would be like an element, well, like 1 or 2 elements that are experiencing peak stress, instead we look at the element that is experiencing, well, think about it as a histogram, right? So there's a histogram. What stress accounts for 97.5% of our, well, the amount of elements, 97.5% of elements are less stressed than that one measure.
Okay, within the same subject.
Yes.
Just say why you don't get the peak.
We don't look at the peak because there are usually within finite element modeling, one or two elements will have very, very high stress levels as a result of surface abnormalities or just artifacts within our modeling technique. And it doesn't provide tons of value for us to know what maximum value that one random element is experiencing, but rather a more accurate understanding of how this bone is being stressed is to understand what a certain percentage of these elements are being stressed at in regards to failure or failure propagation.
Sandra?
You go back to the next slide.
This one?
Is that the same subject in Met 1, 2, 3 that's going up?
Yes, yeah.
Okay, sure.
Yeah.
Okay, so very nicely presented, and
I'm convinced that you're reducing stress
while running in shoes.
I'm also convinced everybody's running in shoes and it's been 7 years.
So is there less running in shoes?
Is there less running injuries? Not that I'm aware of, but with any type of running shoe advancement or as advancement in training methodologies, if people are wearing these shoes and feeling better, they might be running more. And additionally, our body from both an athletic perspective and also just like a bone health perspective, we respond and adapt to the stresses that we experience on a day-to-day basis. And the reason individuals get injured is because they push their bodies just a little bit past what we experience on a day-to-day basis and what we are used to. So it's the same thing as, I guess, just walking around day to day. Because you have grippier shoes doesn't mean you won't injure your back when you step down on the stair a little bit much. There are still random occurrences that will lead to injuries or user error in which we increase our mileage too much and get injured, which is very common amongst runners. We want to push the limits, want to see what the human body can do, regardless of running level.
I'm gonna summarize what I think you said.
Go for it. That was a little roundabout answer.
If it was a yes, no question. No, you speculate that running injuries are the same, but people are maybe able to run more.
Able to or not, I can't definitively say, but I think people will always try and run the most that they can,
Right.
regardless of what shoe they're in.
And nobody's looked at that.
Not yet.
Look at what? If people are running more than they did before with these new shoes.
Yeah, that's still an open area.
I don't know if people looked at stress fractures either. I don't know if there's.
Well, you look at running injuries, right? Running injuries haven't changed in
They're-
70
They're
years.
relatively constant.
Specific stress fractures. I don't know if it's.
No, that's still a gap in research.
Okay, and then I have a really basic, I don't know anything about modeling question. You're, like, doesn't that bone get load from all over the place, including other bones?
Correct.
Is that included in your?
So models can exist at any form of complexity. The more interactions we give a finite element model, the more places something can go wrong in our calculations or our modeling, as well as just raw resources to compute a model. For the metatarsals, they mainly have that one area of interaction, which is the forces acting on the metatarsal head, both from the toes. So you have this joint force, you have plantar tendons that pull the toe into the metatarsal head, as well as forces from the shoe that are, again, being distributed onto the metatarsal head. To account for these different directions of forces, we have both of these combined into one force vector that we distribute over the entire metatarsal head. So we don't just have a point load, but we apply this force and distribute it over the metatarsal head to try and get more of a realistic result. And in terms of its interactions with bones beyond the base, we essentially just said this bone doesn't move in space for this instant that's being loaded, and fix it in space and assume that all of the resultant forces at the base are being transmitted off the skeleton.
Understood. Thank you.
There's one more question for me. So for your second study, have you started, are you going to look at the third to fifth method or?
Yes, so we'll look at all of them, and we just see the same results that we saw in study one, where 1 and 2 have this difference. 3 through 5 are either very close to equal or have no change.
I was just wondering, because as I stare at this slide more and more, I look at Met 5 and then I just see that there are some lines that are going in the opposite direction now and less people that are showing the same trend. So I'm wondering like if you reduce it at one location and might be increasing it at the other location. So that's why.
Yes, and that's a really common question as well, is like, where is this force going? And at this point, we don't really have an explanation as to where it is going. So they're running at the same speed. We have this reduction in Met 1 and 2. What is happening either further up the skeleton or in different parts of the foot, which would be an important question to answer.
Now that NE5 study
Yes,
was published in Sports Medicine,
it was.
now why would a journal with an impact factor of 9.3 publish something like that?
That is a fantastic question. I do not know.
Wouldn't it be a reason for your supervisor to write a letter?
So sports medicine? Well, we need the results of our study to be published first, and then we can see.
The same journal?
So,
Any other-
it's very difficult to publish in Sports Medicine,
It is.
and then they publish something like that, it is bullshit.
I think they leverage the popularity of carbon fiber shoes and just used a few right buzzwords.
This is being broadcast, and let's just remember that.
Any other last question before we thank Patrick? All right, well, let's thank him for his great job.